Hey everybody, Corey and Victoria here. We are the Professors Du Bois, and this is actually the second video in a short series we're going to do on equilibrium concentrations. So these are going to be the equilibrium calculations of the equilibrium constant, equilibrium concentrations, and all things in between. So if you're having some trouble with this in your general chemistry, you've come to the right place.
Here we go. This is the problem we're going to be discussing. In the first episode, we talked about equilibria and the equilibrium expression, so make sure you go back to that if you haven't watched that yet. So we're going to dive right into this problem. And the first thing we look for and we notice is that we have a double arrow for our reaction, and that means that we have an equilibrium. So we have a forward reaction and a reverse reaction. They're both occurring at the same rate. And that means that we've come to equilibrium, and our K expression means that the ratios of our products to reactants, once it's come to equilibrium, is always a constant. So this constant is K. Sometimes you'll see it as a Kc. That just means we've used molarity to calculate this K expression. And if you see a Kp, that means we can use partial pressures of these gases, if it is a gaseous equilibrium, to calculate K. So this one is a Kc, so we've used molarity. And you can see that we have expressed this K expression, equilibrium expression, as K equals our products raised to the power of the coefficients. So our coefficients become exponents in our K expression, so our products over our reactants. And keep in mind that only gases and aqueous solutions go into the K expression. Leave out your pure solids and pure liquids.
And that's one of the first things I like to check for. I like to check the states in my reaction, and these are all gases, so I know they will all be included. The K, it is a Kc, so that's a concentration, and it's a small number. It's less than 1, and I know that this is a reactant-favored reaction because of that value being less than 1. So at equilibrium, we're going to have more reactant than products, and this makes sense. If you look at the way this expression is, if we had a big number down here in the denominator, our overall K would be small. So the other thing I wanted to point out is I'd like to check and make sure the equation is balanced, and because I saw coefficients, I was 99% sure that this was balanced. I still check. Some of those chem professors out there are really sneaky, so don't get caught up in that. So this question starts out in, they give us, typically you get an initial concentration, and this one didn't. It just said sufficiently large was introduced into a flask.
Interesting. So we're going to set up our ice table. We don't know what that initial concentration is, and in fact, that's what we're going to be solving for. So we're not sure what that is, but it's some amount that allows us to come to equilibrium. And when we do, we have an equilibrium concentration. But first, what do we have for the initial concentrations of our products?
Well, we got to think about this. We have an evacuated vessel, and that means that there was a vacuum pulled on this vessel. There's nothing in it. Not even air is in this vessel. There's nothing at all in it, and we put in NOBr and seal it. So all that's in there initially is the NOBr.
So that means we can put zeros for our concentrations of our products, and you often will have to do that. And if we have 0, we know that our change in our to come to equilibrium is a positive number for our products and negative for our reactants. And remember that for every we use our coefficients to express x. So we're going to express our change with x and use our coefficients, because that means that for every 2 NOBRs that react and decompose, we're going to produce 2 NOs and 1 Br2.
And lastly, well, I should point this out. The K value, the equilibrium constant, was given at a certain temperature, and that's because the K value will change if the temperature changes. But notice here that this experiment was done at the exact same temperature. That's 233 Kelvin. That K, don't confuse that for the equilibrium constant.
Yeah.
It is, but they're just referring to the temperature there, and so it's safe to use that this value in our calculation because it is at the correct temperature. And lastly, we do have an equilibrium concentration of the Br2, and that is 0.198 molar. So I have a column.
I love these. When we have an equilibrium concentration, usually these calculations are a little bit simpler. So we can read this just like an addition problem. The initial plus the change equals the equilibrium. So 0 plus x equals our 0.198. That means we've solved for x. And now that we've solved for x, we can put that right back into our change column and solve for our other equilibrium concentrations.
So I've got 0 plus 2x, so I'm going to take this 0.198 and times 2 to get that equilibrium concentration, which is going to be 0.396. Now over here, I have some large amount minus 2x, but this is actually what we're going to solve for. Now, a lot of times when you're solving for something, you'll call it x, and that would really make this confusing. So I want to use a different term. So why don't we call this, we'll just call this concentration, and I'm going to abbreviate it. And this is what we're going to solve for. Hopefully that's okay.
In our K expression, we have K, so we can put these equilibrium concentrations, known and unknown, into that K expression. So we have 1.37 times 10 to the minus third. That's our given K. And we can put our products in. Make sure to have the concentrations raised to the power of the coefficients. So we have squared there. And that's over our reactants, and that is our concentration variable. And remember that that is also squared.
So we're just going to put concentration down here. And this part I think is really tricky, and you just said it, and I'm just going to say it again because I think it was really tricky, is we have to realize that we take our equilibrium concentrations and put them into the expression, but we raise them to the power of the coefficient. So this is actually the concentration squared because there was a coefficient of 2 out in front there. And that part's really, I think, pretty tricky.
Yeah.
So the thing we're looking for is in the denominator, and that's a terrible place to be. When you're trying to solve for something and it's in the denominator, the bottom part of a fraction, get it out of there. And I say sooner is better. Now I've run out of space on the right, but what I'm going to do is I'm going to multiply both sides by concentration squared, and I ran out of space. I'll put it up high. Concentration squared. So that effectively cancels over here. And if I do something on one side of the equals, I have to do it on the other. So now I've got concentration, that's what I'm looking for, squared times 1.37 times 10 to the negative 3 equals, and now I have my 0.396 squared times the 0.198. If I just do that in my calculator, the 0.396, I'll square that, and then I'll go times 0.198. I get this value, 0.0310495.
So why did you carry so many digits there?
Well, I like to just round to sig figs at the end.
Yeah.
When I'm all done out. Now, technically here, it looks like this is going to be a 3 significant figure answer. I really only need to carry 4 significant figures, but I just got carried away. Okay, so to get concentration by itself, I'm going to divide both sides by the 1.37 times 10 to the negative 3. That'll cancel on the left, and then I'm going to take that value divided by 1.37 times 10 to the negative 3. I'm just going to scroll this up. This might look a little weird.
This looks like a 7, and that one looks like...
That's a 3.
Like a 2.
1.37 times 10 to the negative 3. So what do I got? I got concentration squared equals, what do I got for a value there? 22.6639. Okay, now what do? You know, I've got this squared. Well, the way we get rid of that squared is we use the square root. If I take the square root of that, that is going to just equal concentration. But again, like I said before, if you're going to do something to one side of an equals, you have to do it to the other side, then you're okay. So I have to take the square root of the 22.6639 to get my final concentration.
And now we're going to round to our three significant figures of 4.76. And this is a concentration. It was a Kc, so we used molarity. So these are in molarity. And that's that. That's how you solve for that. Nice job.
That's a tricky problem. It's a little intimidating when they just don't give you an amount and just say a large amount. I mean, it's kind of hard to think through. Well, okay, where do I go from there? But you can see this is very possible using the ICE table, because if we just have the equilibrium concentration of 1, either a product or reactant, we can ultimately find the others.
So thanks for tuning in. We will continue this series talking about and discussing how to solve these equilibrium problems. And so stay tuned and join us for episode 3.